All right, we'll go ahead and get started. And I'm JT Mesite. I'm with the Colorado Ready Mix Concrete Association. If you go to the next slide for me there, Kevin. We've got Kevin Kane here in the office that's going to be presenting today. But before we do that, I just wanted to reiterate to everybody that's on. I know pretty much all of you guys are members of CRMCA, but if you have clients that would see benefit to be members as well and get their and use their voice to really improve the industry, please have them reach out and either to myself or go to the more information page at crmca.org and get them part of membership. So we are here for Tech Tuesday as a series as part of the Tech Tuesday series. If you could go to the next slide. We've got this. We're halfway into the second year of doing these Tech Tuesdays for CRMCA, and hopefully these are helping with ongoing changes and issues that are going on, and really hope to really specifically today with Kevin Kane here to talk about specific issues that could really improve the industry going forward from where we're at and where the industry and the global political climate really is going forward anyway, no matter what side you're on. So with that, I'm going to hand it over to Kevin. I will let him introduce himself and go from there. But in the meantime, or once we get to that, if you could, during the presentation, Kevin does ask that you just interrupt him. If you cannot unmute yourself, please do utilize that raise hand button on the Teams format, or put a question in the QA. Honestly, we'd rather the conversation be vocal here, so don't hesitate to harass him for any comments that he's making in regards to his presentation. So with that, I'll hand it over to Kevin.
All right. Thanks, JT. My name is Kevin Kane. I work for AmRise. I work in technical services. So I do technical services for the Portland plant in Colorado and the Double Slide plant in Utah. I cover New Mexico, Colorado, Wyoming, and Utah. And I'm happy to be here today. Happy that JT invited me to do this. It's my pleasure to present on this topic here, which I think is a really hot topic right now, and that's sustainable concrete mixture design. So like JT said, if you have any questions, just shout them out or raise your hand. I'd rather take the questions one at a time than the firing squad at the very end, but I think it's a friendly audience, and I think we'll get along just fine. So I'm looking forward to doing this for you. Okay, the outline. Why sustainability? We're going to cover some background stuff on sustainability, the role that cement and concrete plays in sustainability, and then we're going to talk about the role that fundamentals play in sustainability. We cannot forget our fundamentals. We cannot be sustainable if we do not execute our fundamentals, kind of like blocking and tackling in football. We're going to talk about reducing the embodied carbon of concrete mixtures, and then at the very end, I'll share some resources that I've used to put these slides together. And I'm also, during the course of the presentation, I'm going to refer back to the Tech Tuesday presentation presented by Zach Ballard back in April and Jim Schneider back in June. In fact, I may even stole some of their slides. So, but I want to tie the whole thing together on proportioning, materials, and what we can do as our industry to reduce the embodied carbon of concrete mixtures. So with that, let's take it away. Why sustainability? What is all this sustainability talk? Well, according to the UN Environmental Global Status Report, the world is projected to add 2.7 trillion square feet of buildings by the year 2060, driven by soaring needs for housing and infrastructure. And that's add 2.7. That's an additional 2.7, which is going to double our current global building stock. That's a lot of building. The UN report urges the building industry to reduce embodied carbon of building materials, and the UN report also urges building designers and owners to reduce the operational carbon by designing disaster-resilient buildings for the future with zero energy consumption. I want to make the distinction of embodied carbon versus operational carbon. Embodied carbon means all the carbon that went into producing a given product, whether it's concrete or cement or lumber or steel. Operational carbon means the amount of energy that took place after the building went into service. So we're going to be talking mostly about embodied carbon, but I am going to start off with an example of operational carbon. To meet this challenge, the NRMCA adopted Architecture 2030, the challenge in 2012. The goals was to reduce operational carbon and embodied carbon from the built environment to net zero by 2050. Now, reducing these carbon emissions is the key to addressing climate change. Now, it doesn't really matter who you voted for, where you lean politically. Doesn't matter if you voted for Trump, doesn't matter if you voted for Biden. Doesn't really matter where you sit on the political spectrum. Sustainability is a business necessity. So keep that in mind. A lot of people get emotional about climate change and global warming, but let's just keep this on a business, how it affects us as a business. In 2021, the NRMCA reaffirmed its commitment to reducing its carbon footprint by supporting the PCA roadmap, which is actually now the ACA, for American Concrete Association. They changed just in the last couple months to the American Concrete Association. So the NRMCA reaffirmed its commitment to reducing its carbon footprint, supported by the ACA roadmap to carbon neutrality. Now, sustainability is therefore a strategic business necessity. Like I said, doesn't matter how you feel about global warming or climate change. It's a strategic business necessity. So let's talk about some of these sustainability projects. And the one that pops into my mind first and foremost is the brand new Populous Hotel in Denver. Now, when the architect and owner first met, they wanted to get a feel for where they were building this hotel. So they chose to go to Aspen, Colorado, and kind of get a flavor for Colorado to kind of guide their decision-making on what this hotel should look like. And I'm glad they chose Aspen, Colorado, and as opposed to like Clear Creek in Commerce City, because the hotel may have ended up looking like a shanty town of tents and abandoned RVs. But they chose Aspen, thankfully, so they chose the Aspen Populous. And Aspen, the aspen tree is from the genus Populous, hence the name Populous Hotel. And you can see in the picture there, everybody who's seen aspen trees know it's a very distinctive looking bark. So they designed the facade or the facade of the building to kind of look like a populous. And it's a very interesting hotel. It's the only hotel in the United States that's carbon positive. So that's pretty cool. So if one guy did it, probably going to be some more businesses that want to do it. There's probably going to be a lot of people who want to stay in a hotel that's carbon positive. It's kind of a neat thing. And they did a lot of neat things along the way. They did ecological restoration. So whatever carbon they weren't able to reduce during the construction phase of the project, they purchased carbon credits by designing construction techniques and through large-scale planting efforts all over the country. So they did a lot of tree planting to offset the carbon that they were creating in the construction of the hotel. Another kind of cool thing. Here's one of the rooms, and the thing I really like about this hotel is there's a lot of exposed concrete. So it puts our product right out there as a showcase. And some people may go, my God, why did they pick exposed concrete for the roofs? Well, there's a reason for that. We'll get into that in a couple slides. But so it's a very unique hotel. They have a carbon positive dashboard. So anybody can go onto their website and see where they're at on their carbon positive venture. Right now, they're at 117 carbon positive status. And down there at the bottom, you see this the offset activities. They They went negative, so they had to capture some offsets on this. So they went around the country and they planted. It's like, here we are. Here's the Populous Hotel in Denver. Well, there's a little dot way over here in Gunnison. They're doing a lot of tree planting and reforestation in Gunnison. They're doing some reforestation efforts in Massachusetts and Vermont, and they're doing some tree planting down here in North Carolina. So there's a lot of creative things they can do to maintain a carbon positive thing, which I think is really kind of neat. So that answers the question, why sustainability? It's a strategic business necessity. If one business did it, if they have customers, their customers will take these ideas to other businesses. This isn't gonna go away. Everybody is gonna be attracted to building structures like this. So that brings us to us, the cement and concrete industry. Now, how are we viewed right now? Well, kind of negatively, right? So look at some of the glaring headlines from the media. Concrete, the most destructive material on Earth. The cement industry produces more CO2 emissions than most countries. It may not survive. We may have to abandon concrete to fight climate change, architectural experts say. So it's kind of doomy and gloomy out there. Not a lot of good news. So this kind of reminds me of the scene from Apollo 13 in the middle of a crisis, where Gene Kranz, he was in charge of all the nerds at Mission Control in Houston. He said, let's look at this thing from a standpoint of status. What do we have on the spacecraft that's good? We got a lot of things that's good about concrete. UN report urging building designers and owners to reduce their operational carbon by designing disaster resilient buildings. What's more disaster resilient than concrete? You know, we've all seen the images of the wildfires in California, the flooding down the Guadalupe River, the hurricanes down the Gulf Coast. Concrete is a very disaster resilient building material, and we should play that card. Concrete is also a low VOC emitter, volatile organic compound emitter. It's a low emitter of VOCs. That's why the Populous Hotel chose to leave a lot of the concrete exposed and not cover them with wall coverings that do emit VOCs. Concrete also absorbs CO2, which years ago we didn't think that was that big of a deal. Well, we think it's a pretty big deal now. In fact, there's some research that says during the lifespan of a building, the building will have absorbed half the CO2 it took to build the building. So that's a pretty neat attribute. Provided your reinforcing steel has the proper amount of cover on it, that's really a good attribute. So concrete absorbs CO2. That's a positive. So what are the negatives? Okay, concrete, it's the most man-made substance. It's the most used man-made substance on Earth. It's not going away. You're not going to be able to have civilization without concrete. Now, cement manufacture contributes to 10 to 12% of total CO2 emissions on Earth. So we're one of the big polluters on Earth. So to lower the embodied carbon of concrete, we must lower the embodied carbon of cement. And here's an example of a concrete mix design. This calculation was published on the CDOT white paper on the development of CDOT embodied carbon benchmark limit values for the Buy Clean Colorado Act. And if you look at the calculations here, the cement is responsible for 90% of the global warming potential of this particular concrete mixture. So to lower the embodied carbon concrete, to lower the embodied carbon of concrete, we must lower the embodied carbon of cement. So how do we do that? Well, let's get into a cement plant. This is a typical cement manufacturing facility. It's a highly complex process. And it all starts here in the quarry with very heavy machinery, very heavy excavating equipment that burns an awful lot of diesel fuel. And then we go to a primary crusher, which operates off a very large, high horsepower engine. Then we go to a raw mill that has an even bigger motor, 6,000 horsepower at the Wholesome Portland plant. Then we go into the pyro process of the thing, the kiln and preheater and pre-calciner. So this is where most of the energy is required to drive that calcination process. We're mining calcium carbonate, and we have to convert it to calcium oxide. And in the process, we release 40% of its original mass in CO2. So the conversion, the calcination of the limestone to calcium oxide is a big polluter. And the fossil fuels that it takes to get the kiln to the 1500 degrees centigrade temperature to get that calcination process kicked off, that is also a big CO2 emitter. So you can see the bulk of the CO2 emissions come from this little section right here. It's all in the pyro process. So we're not going to put a dent in anything by converting our equipment to batteries or to natural gas. We're not going to make a dent if we put a new motor in the raw mill, something a little more high efficiency. We're not going to make any change if we try to save some energy over here at the cement mill. It's all right here. It's all right here in the kiln. It's the pyro process that emits the CO2. So that's where it's at. So to lower the embodied carbon of concrete, we therefore must lower the embodied carbon of the cement. Now, over here on the left, let's look at ASTM C150 Type 2 cement post, say, 2005. Post-2005, ASTM C150 Type 1-2 cement had 5% limestone, roughly 4% gypsum, and it was ground with roughly 91% clinker. So it's this 91% clinker in ASTM C150 Type 2 cement post-2005. ASTM C595 Type 1L cement has 10% limestone, or up to 15% limestone. Presently, most producers are around 10% limestone. And again, roughly 4% gypsum. And now we've reduced our clinker factor from 91% to 86%. So it's this reduction in clinker percentage, aka also known as the clinker factor. That's what lowers the embodied carbon of cement. So that's the only lever we have to pull right now on the cement side. So Colorado passed a Buy Clean Colorado Act in January 1st of 2025, and they set these benchmark limits on global warming potential of our concrete mixtures. So for everyday Class D concrete, which is the bulk of our CDOT work, the global warming potential limit is 365.1 kilograms of CO2 per cubic meter. Now this document right here, this table 8.3, is published in the ACI code 323, which was just published last year in 2024 on low carbon concrete. This is what their benchmark values are, but they express their benchmark values in kilograms of CO2 per cubic yard. Does anybody else think it's weird that we don't go pounds per cubic yard and kilograms per cubic meter? Why do we use kilograms per cubic yard? Kind of an awkward conversion. So if I convert the benchmark values for 4,000 to 5,000 PSI, and incidentally, ACI code 323 derived these values right from the NRMCA benchmarking that they did back in 2023. So if we convert cubic yards to cubic meters, we take the 274 kilograms of CO2 per cubic yard, multiply it by 1.308, we come up with 358.4 kilograms of CO2 per cubic meter. Oops, not square meter, cubic meter. And that's pretty close to what CDOT came up with. So these are very obtainable values, and we've been doing these for a while. So in fact, the Rocky Mountain region, if you look in this document, ACI 323, Rocky Mountain region pretty much is already the lowest or lower on the global warming potential than the other regions around the country. So we're already a little bit ahead because, Colorado is a pretty green state. So let's talk about the role that fundamentals play in sustainability. So concrete, it's kind of hard to get around this, but concrete with higher variation with respect to compressive strength performance, concrete with higher variation will need more cement than concrete with lower variation. Kind of hard to get around that. And from the ASTM C917 report, Tony Fiorato wrote, to minimize the variability of concrete, it is necessary to control the uniformity of constituent materials as well as the uniformity of batching, mixing, transporting, placing, and curing. Tony Fiorato is a pretty smart guy. He pretty much nailed it. If you want low variability in concrete, you've got to control the uniformity of your materials and your processes. So You as ready mix producers, insist on good quality materials that are consistent. Insist on consistent processes from your operational departments, measuring, batching, mixing, transporting. And if you're on the testing agency side, if you're on the QA side of the business, you want to insist on good quality control and good quality assurance testing. Whoops, I missed one. And let's also promote good construction practices. And this is kind of an important one because this seems to be a hot topic right now, is good construction practices, because a lot of contractors are really struggling with the changes that have been made from concrete that was made with ASTM C150 Type 1-2 cement to now ASTM C595 Type 1L cement. So we really need to get out and promote good construction practices so we don't have so many problems associated with finishing problems, plastic shrinkage, and scaling in the field. And I'm sure this is probably going to come up in Q&A, is yes, concrete made with Type 1L cement is a little different, doesn't bleed as much. So construction practices, if they weren't important before, boy, they sure are important now. Going back to what Zach Ballard presented, you can't control what you don't measure. So low variability, you're going to make money. High variability, it's going to be tougher to make money. So if we look on the left side of the scale here, here's our required 3,000 PSI. If you have low variability, you only need to average, in this example, 3,326 PSI. If you have high variability, if you don't have good control of your materials and your processes, you have to average a much higher compressive strength to satisfy this 3,000 PSI mix requirement. So low variability is good. High variability, bad. It's going to cost you more money, and it's going to take more cement, which is not in line with sustainability. Insist on ASTM standard adherence. Boy, oh boy. I've been doing this for, gosh, it's 35 years now, and we're still talking about adherence to ASTM standards in testing. And the elephant in the room is always the initial curing. And it's a challenge for the testing agencies to supply the proper curing facility for every job they're going to test that day. But you got to get out in front of these things in the pre-construction meetings. Post-construction meetings are not the time to talk about initial curing. Talk about those in the pre-construction meeting when it can be decided who, how, when, where are they going to put the initial curing facility. If we take a look at this study that we did back in 2014, this was a test fest, a CRMCA test fest event that we did in Grand Junction, Colorado. This is 3 sets of cylinders cast from the same sample of concrete, and we varied the initial curing conditions. The first set of cylinders was put in a Rubbermaid cooler filled with water. Not very scientific. A Rubbermaid cooler that you could, at that time, you could have bought from Walmart for 20 bucks. You fill it with water, you put your cylinders in there, and you measure your min-max, and this is well within the specification limit of 60 to 80 degrees. And this is the resulting compressive strength of the properly initially cured test specimens. That another set of cylinders from that same sample of concrete, where we put them in a Rubbermaid cooler with no water for a 24-hour initial cure. And look what the temperature went up to. The heat of hydration from the concrete cylinders was detrimental to maintaining that 80-degree maximum temperature. It went up to 105 degrees, and there was a resulting decline in the later age strength development. We all know this, and yet we still have the problem. And then worse, if you just take the cylinders and leave them into direct sunlight. We have pretty intense solar radiation here in Colorado. Look what happens. It was only 93 degrees that day, but these cylinders were left out in the sun, and look what we did to our compressive strength compared to the properly cured cylinders. So we must insist on adherence to ASTM standards. And I know everybody's been hearing it forever. We're going to keep beating the drum until we get 100% compliance, because it's all for nothing on sustainability if we don't do the testing correctly. And it's not always the testing. It's not always a test. Sometimes it's us, and we have to admit that. Here's 2 mixes that Dave Figursky and I ran back in January of 2025, where we wanted to test some of the plastic and hardened attributes of our Utah plant, Devil Slide in Utah, with our Type 1T cement. So we made our first mix. We gathered an aggregate sample from a local producer right here in the Front Range. We didn't particularly like the sample of coarse aggregate that we got. We kind of, it was, the gradation was way too fine. It was pretty dirty, but we ran the mixes anyway. And we ended up having to discard the whole series because we didn't like the results we got. We went out and got another sample of the same source of aggregate. This time the quality of the aggregate was right where we wanted it. And look at the difference it made in the proportions. So both of these proportions produced about the same workability. Look at the difference in water content. This mix, it took 335.6 pounds per cubic yard to get that 3 1/4 inch slump. This mix with properly graded and proper clean aggregate that met the specification, it only took 315.3. And we actually had 10.8 pounds of water left over. Produced the same amount of workability. Look at the difference it made at 28 days in the compressive strength, over 1,000 PSI. So it's not always the testing. We have to insist on adherence to standards of testing. We also have to insist on adherence to standards of our materials that we're making our concrete with. This was on John Belkowitz's LinkedIn page just last week. And with respect to the role that fundamentals play in sustainability. Actively managing problems versus reacting to problems is so important. Stay a step ahead rather than 3 steps behind. Recognize the root causes to the common problems and take the steps to minimize their reoccurrence. Think the process through and manage your obstacles and challenges. Removing and replacing concrete is certainly not a sustainable practice. Root causes to common problems. What's a common problem everybody's having right now? Are we having problems making our concrete, controlling our concrete? No, but our customers, the contractors, the finishers, they're certainly having some common problems. So that's where we get back to the construction practices. If construction practices weren't important before, they're sure important now. And none of the practices that we're advocating are any different than what they were before we made concrete with ASTM C150 Type 2 cement. It's just that not everybody was following them by the book. The book is written by a reason, for a reason. They're written by very accomplished professionals that know their business. These aren't just people that read and write books and never get out of the office. These are these professionals that write these construction practices. These are accomplished professionals that know their business. We have to follow the best recommended practices in the field. Okay, reducing. Let's talk about reducing the embodied carbon of concrete mixtures. And like I said before, I'm going to be throwing back to previous presentations. One that Zach Ballard did in April, and the other one that Jim Schneider did back in June. So let's go back to Zach's example on how he walked us through the steps in proportioning using ACI 211. When he got to step 8, which is pretty much the final step, that's the final step in the proportioning, but your work is not done yet. So he came up with a concrete mix that had 708 pounds of cement, 340 pounds of water, with these proportions of coarse aggregate and sand by following the steps in ACI 211. But your job is not done. Now you have to go put them in a lab mixer. But first, I'll bet there's not many ready mix producers out here that have a mix that has 708 pounds of cement and 340 pounds of water for a 5,000 PSI non-air entrained mix. And there's a reason for that. They made adjustments. So in selecting the water content, yep, you follow step 3, estimation of mixing water and air content. And if you have a 3/4 inch aggregate and you want a 3 to 4 inch water slump, you're going to need about 340 pounds of water. But there are some exceptions. We need to follow these adjustment factors. So if you're using a rounded aggregate instead of a quarry stone, take off 8% of that water. If you're using a water reducer, take off 5%. If you're using fly ash at 20%, take off 20% water. So let me show you what happens to this original 340 pounds of water when we take these factors into consideration. So we take the 340 that Zach came up with, but we're going to say, yeah, but we're not going to use a quarry stone. We're going to use a rounded river rock. Okay, divide that by 1.08. Now you're down to 315. but we're also going to put a type A water reducer. Okay, let's take off another 5%. Now you're down to 299. Well, that number should look familiar to a lot of us. That's pretty much where our non-air entrained straight cement mixes are. Now, what do you do with this number now? Well, now you have to recalculate your cement content. So you take this 299.8, divide it by the water cement ratio that you needed for your 5,000 PSI, which was the 0.48. And that came from the table values from the ACI 211 document. Now you're down to 625 pounds. So even that, okay, are you done yet? No. Now you got to run your 3-point curve. Then you got to evaluate your results. And then you have to reselect your water cement ratio based on your actual data from your materials. So you have to satisfy whichever mix, and you can interpolate between intermediate values, but you're looking for that 5,000 PSI mix needed to attain 6,200 PSI to satisfy the ACI 301 4.2.3.4C requirements. So you look at your 3-point curve, you recalculate your cement content based on the new water cement ratio that you've selected from your 3-point curve, and then you start over, run another 3-point curve and reevaluate. And you keep doing this until you're satisfied that you've got a mix that you can produce and reproduce in the field that'll generate good results for your customers. So there's nothing easy about this. On paper, it's easy, but that's not the work does not end on paper. The hard work begins at that point. But ACI 211 is a great guidance document, but it's just the first step in the process of proportioning concrete mixtures. A little pro tip too: you can avoid that whole accounting for water reducer if you choose to, instead of selecting, okay, let's say you needed to design a 4-inch slump concrete mixture. These table values are based on the water slump that's generated, not considering the water reducers. So in my experience, if you're using a type A water reducer, this is where you want to be, in this 3 to 4-inch water slump range. If you're using a high range water reducer, you could go down to a 1 or 2-inch water slump. And so you can cut out all that math by selecting your water slump and then verifying that you got it right. But if you're using high range, a good water slumps between 1 and 2. If you're using a type A or mid range, a good water slumps between 3 and 4. We get in all kinds of trouble when we end up making -2-inch water slump concrete. And by -2, how do you measure a -2 water inch slump concrete? If you're 2 gallons per yard away from your first slump measurement, if your mix is so dry that you have to add 2 gallons per yard just before you first produce your first 1/4 inch of slump, you're in negative slump range, and that's where the problems happen. Your mix is water starved, so you got to have the right amount of water in the concrete. That's a pretty important fundamental. So then Zach talked about aggregate packing and aggregate grading. So a traditional mix design using ASTM C33 sand and ASTM C33 coarse aggregate, just 2 aggregates, you're going to end up with a gap graded aggregate, but it works just fine. You can make most concrete mixes with just rock and sand. That meets ASTM C33. You can make concrete just fine all day long, every day. We did it for years. But you can optimize and make more sustainable and reduce some of that paste content if you optimize your aggregate grading. Now, that's where you take more than 2 types of aggregate: a fine aggregate, a coarse aggregate, and an intermediate aggregate, and find that well-graded version of this. And if you can do this with your aggregates, you're going to use less paste, you're going to use less water, you're going to use less cement, and you're still going to have good results. So that's what's meant by optimizing your aggregate. There's a lot of benefits to optimizing your aggregate, sustainability being one of them, because as you optimize your aggregate, you're going to be able to reduce your cement content. And then these are some of the tools that Zach talked about we could use. This is the old coarseness factor and workability chart that Shillstone developed many years ago. And if when you plot your combined gradation of your coarse and fine aggregate, you ought to be living in this zone 2. If you can make concrete in zone 2, you're going to be okay. If you're up here in zone 4 or zone 3, you might have some issues with your concrete. So you want to use these tools to get the right proportions of aggregate. Here's the haystack curve. This one will give you fits. Try and get into this haystack with just rock and sand. Pretty tough to do. You're going to need another aggregate. Same thing with this tarantula curve that they developed. Tyler Lay down at Oklahoma State University. He developed this tarantula curve, and it's very good. It's very effective. But you're going to need an intermediate aggregate, if not two intermediate aggregates, to find your way into this tarantula curve. But when you do, boy, you can really optimize your aggregate grading and reduce your cementitious content. And then there's the old 0.45 power curve that the asphalt guys, and there's lots of tools. You can use any one of these. You figure out which tool works for your tool bag, for your organization, and use them. These were really good points that Zach made in his presentation back in April. And by the way, if you're like me, I need to watch a good movie 3, 4, 5 times, especially a complicated movie with a complicated plot with a lot of plot twists. I can't watch it one time and catch it. I got to go back and watch it again. My wife, she can watch a movie and she can tell me what's going to happen before the end. I have to watch a movie three to four times to piece it together. Same way with presentation. Go back. CRMCA has a YouTube channel that you can go back and look at these presentations, because you may be looking at your phone. You might be distracted by an important text or an important email. Go back to the YouTube channel and watch Zach's presentation, watch Jim's presentation, watch this presentation again. It might take a few times to get through it. Now, when you do go to YouTube and watch the presentations, be advised, you're going to be interrupted about every 3 minutes by a commercial, but that's okay. Just be patient. A few seconds will go and you'll be able to skip the commercial and get right back to the good stuff. Supplementary cementitious materials. What about pozzolans? Oh my gosh. When I first got in the business 35 years ago, we basically had one pozzolan, and that was Class E fly ash. Cut my teeth on Class E fly ash. Now it's kind of hard to find Class E fly ash. Class F fly ashes came around in the late 90s. And when I first switched from Class C to Class F, I was wowed by the benefits of Class F. Class F fly ash, while it doesn't have the strength activity of Class C, has a lot of other attributes: sulfate resistance, ASR mitigation. Class F fly ash is much easier to use. Now, fast forward 25, 30 years. Now, supplementary cementitious materials they're not scarce, but they're getting difficult to get. They may be getting scarce, but we're also going to get a lot more choices. There's a lot of different supplementary cementitious materials available now today, and there's a lot on the horizon. Now, none of these are overnight fixes, but it's good that the work is being done, and that at some point in the not too far distant future, not tomorrow, but in the not too far distant future, we're going to be able to use a lot more supplementary cementitious material choices than we currently have now. And Jim Schneider, wow, he did a great job of laying out all the different innovations in SCMs, basalt, mine tailings, biomass, all these new innovative supplementary cementitious materials, recycled glass from this positive material. That positive, and a little play on words, it's a pozzolan. It makes positive carbon impact. So there's a lot of interesting thing about all these new materials. Mine tailings, NREL. Go work with the people at NREL. They've got an amazing concrete lab there, the National Renewable Energy Laboratory, right here in Golden, Colorado. What a facility. My gosh, they've got scientists, and very talented scientists from all over the world that work there. And they make concrete just like we do. They have a concrete lab just like we do. Reach out to these folks. They are testing some amazing materials. They are way ahead of us on R&D. And we should be networking with NREL to find out what's, again, not overnight fixes, but on the horizon. It's exciting. Blue Planet Systems Corporation. They're doing stuff with working with NREL, and they're taking all these interesting materials. And if you go back and look at Jim's presentation, you'll get a little bit more idea, and then you can research it on your own. Microalgae. Who knew? To make Portland cement, okay, so we get limestone from a large quarry, but some species of single-cell calcareous microalgae can be biologically grown. It can biologically grow limestone through photosynthesis, just like coral reefs. Creates a net carbon neutral way to make Portland cement. So all you need is 1.1 to 2 million acres of open pond systems, hopefully located by your cement plant. But again, Not an overnight fix, but it's really cool that a lot of these scientists are working on this stuff. So a lot of neat things coming our way, and there's going to be more neat things coming our way. Cellulose nanomaterials. I wish John Belkowitz was on the line so he could nanometers. What's the difference between a nanometer and a micron? I believe a nanometer is 1/1000th of a micron. A cement particle is 30 microns. Look at how small they're talking here on these nanoparticles. Little teeny tiny particles that get into the cement particles and increase the hydration products. Really neat science. What about pozzolans? Okay, so it's a daunting list of possibilities. And again, a lot of these are not overnight fixes. Now, it's going to depend on the materials that are available in your area. It's going to depend on how many storage silos you have available. That's always the bottleneck. Not everybody has 8 silos to put cement and fly ashes in, right? Most people have what? 2 or 3 at the most. It's going to depend on specification acceptance. It's exciting to bring new products into the market. It's a challenge to get them adopted into specifications. And it also depends on how hard you want to work. None of this is easy. None of this is quick. It's all back-breaking, dirty work. But it depends on how hard you want to work. So where do you start? You start with concrete trial mixes. Start in the concrete lab. Measure things. Measure things like Zach talks about. You can't control what you don't measure. Start in the concrete lab. Measure the slump life compared to a control mix. Measure your time of initial and final set compared to control. Measure your bleed water compared to control. We never used to pay much attention to bleed water. We kind of took it for granted until we started realizing that, wow, type 1L cements don't bleed as much as type 2 cements. So then we started really paying attention to it. But time of initial and final set. The worst thing you could have when you don't have a concrete mix that supplies a good amount of bleed water to the surface is a concrete mix that's very retarded and takes a long set. That's not a good combination. Long set time and little bleed water is not a good combination because what do we get then? We get plastic shrinkage potential. When we did the Ocean Journey Aquarium back in 1996 or 97, that was a very challenging 6,000 PSI mix with, at that time, the only high-range water reducer available was an old naphthalene formaldehyde sulfonate. And its effect on that concrete mix was it was very retarded. And I measured it, 16 hours, 16-hour initial set times. And I sat there and measured those well into the night, well into the early morning. But I was able to go to Hensel Phelps and said, oh yeah, about this mix you're going to be building this aquarium with. You really need to know this. It's painfully slow to set. And they weren't happy. But it gave them a clue on how they were going to time their forming. And they would actually do some wall placements where they would order a pump. The pump would come in, pour the first lift. The pump would leave, and another pump would come back 4 hours later to do the second lift. That's how difficult that mix was to work with. But we wouldn't have known that if I hadn't measured the time of the initial set. Hardened concrete properties, 1, 3, 7, 28, 56 compressive strength compared to control. Drying shrinkage, permeability, freeze-thaw durability, and de-ice scaling resistance. You got to measure these things. Sulfate resistance, ASR control. It's a lot of work, a lot of time, especially sulfate resistance. That's not a quick test, is it? You don't get any results for 6 months. ASR is pretty quick, but sulfate resistance takes a long time. In fact, if you're going to be on S3, you got to wait 12 months. So there's a lot of work and a lot of time that goes. It's a huge commitment, but you got to be willing to do the work. So start in the concrete lab. What do you do next? Do you go right from the lab to the field? Nope. Let's do some test batches at the plant. Let's make sure we can reproduce in the plant what we made in the lab. Do mock-ups with contractors. Invite your contractors and say, I want you to test this new mix that I've come up with. Here's the application. Here's the rationale for it. I want you to use it and give me feedback on it and give me an honest assessment so I can make any adjustments necessary. Collaborate. Collaborate with your suppliers. Collaborate with your contractors. Collaborate with the project team. You can negotiate on a carbon budget for the project. If you have a high-rise building that has 5,000 PSI PT deck mixes, post-tension deck mixes. What do they want? They want 3,000 PSI in 3 days. Not really. They want 3,000 PSI in 2 days. They'll tell you 3, they mean 2. Is that where you want to compromise the mix for a carbon budget? Maybe you can negotiate the carbon budget with the project team. Say, let me do a higher GWP mix for the PT deck slabs. In exchange, I'll do your walls and footers with 56-day compressive strength with a much lower GWP than what you specify. So you have to be a team player and work with the project team, work with your suppliers, work with your contractors. Now, here's a mix. I'm just about wrapping up here. So here's a mix that hasn't seen the light of day since I ran it. I think I've only showed this mix to one other person. Well, actually, Tom Pello and Tom Green. But this mix never made it out, never made it past the laboratory. I ran this mix in 2000 when I worked at Aggregate Industries. And the reason I ran it was because I was bored and I was poorly supervised. No, just kidding. I was very curious, and I like to make concrete. I like to throw a lot of stuff against the wall and see what sticks. So here's where my materials were. I took C150 Type 2 LA cement from, at that time, it was Holnam. Class F fly ash from, at that time, was ISG Resources. I took microsilica from Master Builders. I took a pea gravel and a sand right out of the Platte River pit from Aggregate Industries Thornton pit. I used Master Builders 3000 FC. Is Master Builders Micro Air, and just for kicks, I put in an SRA, Tetragard, and I put in a corrosion inhibitor. Now, are we ever going to have to make that kind of concrete mix? Probably not, but like I said, you don't know until you try it. Let's see what we get. So I put together this mix, only 476 pounds of cement. Look at how much fly ash I got in there, 30% fly ash, and I got another 7% of silica fume on top of that. I've got my high range water, and I don't have a ridiculously low amount of water. That is a low water content. That's probably 0-inch slump concrete. But for this, for high strength air and train concrete applications, you're not looking. This is not going to be drive pans and sidewalks. This is going to be some kind of structural element. I put in 1.5 gallons per yard of the shrinkage reducer. I put in 2 gallons per yard of the corrosion inhibitor, and I got these results in my physical properties. 6.5-inch slump, 7% air, 140 pounds per cubic foot. And that water cement ratio for this amount of cementitious is not ridiculously low. A 0.38 is not terribly low water cement ratio. I measured my initial set because I wanted to know, because that's gonna mean something to the contractor who may have to build something with this concrete. At pretty normal concrete set times, 4 hours and 45 minutes. Look at the drying shrinkage I got from the 2 gallons, or from the 1.5 gallons of Tetragard. I got a 0.034 drying shrinkage at 28 days. Look at the compressive strengths I got out of air and train concrete with a concrete mix that only had 476 pounds of cement in there. At 56 days, I had over 10,000 PSI. I don't know what we would do with this mix, but that was 25 years ago. Like I said, this mix has never seen the light of day. But we could always go back to it to guide us. Do we need the 53 pounds of silica fume? Probably not. We could maybe substitute that with a nano-silica. Maybe we get John Belkowitz to help us with that. Do we need corrosion inhibitor? Probably not. With these kind of compressive strengths, the permeability is going to be really low. We may not need corrosion inhibitor. But these are the kinds of things you do. You don't know till you try. You got to be creative. You got to be willing to do the dirty work. So that's where I'd like to, not to toot my own horn, but this was this was a really cool mix to look back at. I'd almost forgotten about it. Thanks to Dave Fergursky for saving all my work from when I left Wholesome back in 2019. He saved my hard drive, and I was able to recapture this data. I was like, wow, I'd forgotten I'd even done this. But anyway, that takes me to the end, and I want to go through some of the resources that I used. First and foremost, CRMCA. Here's the sustainability page of their website. Concrete.org. This is the page to ACI 332 on, no, 232 or 332?
232.
232 on low carbon concrete. That document just came out. It's the first issuance of that document, 2024. It's good to read it. NREL, reach out to these folks at National Renewable Energy Laboratory. These folks are doing some amazing things. And again, none of what they're doing is going to be used tomorrow, but we may use it in 5 years, 10 years. You'd be surprised how fast 5, 10 years and how fast 5 and 10 years goes by. Here's the CRMCA YouTube channel. if you want to go back and watch this presentation or Zach's presentation or Jim's presentation or any of the Tech Tuesday presentations, this is where you'll find them. CDOT, this is where you'll find their white paper on those on the GWP limits. And then finally, this concrete.org, this is where you'll find that ACI article that we published in August of 2015 on improving the quality of concrete testing. The three authors were guys named Dave Figursky, Todd Laker, and some guy named Kane. Check it out. It's pretty good reading. That's a shameless plug for my own paper, but I'm pretty proud of that paper. So with that, we're about 50 minutes in. That's kind of what I figured it might take. I hope I still got people on the line. If you have any questions, now is your time to ask questions, and let's keep it friendly.
Thank you, Kevin. Yeah, everybody has the opportunity to unmute yourselves if you have any questions or comments. So please don't hesitate to jump in and ask any questions now. Otherwise, we will say thank you to Kevin. And again, I'll just say, it's like utilize that QR code that's on the page right there to keep up with all of our events. CRMCA is in the process of getting an update to our website, so it'll be easier to find a lot of these documents as well as the YouTube page. And we will be sharing this presentation on YouTube, on that YouTube channel that Kevin already mentioned multiple times. And I will say that I did not prompt him to reference that stuff at all.
I want to say one more thing. Hi, Mom. I'm going to send the link to her so she can see me on TV. That's a big deal for her.
Absolutely. So any comments or questions from the group, please don't hesitate to jump in.
Hey, Kevin, I have a question as far as the high variability that you were talking about in proportions. Who's really responsible for controlling the variability, and how are companies policing that to make sure that it's, their variability is low?
Oh, that's a great question. Everybody has a contribution to that standard deviation. Material supplier, we have normal variability, we have abnormal variability. There's normal variability in all materials, whether it's cement, fly ash, aggregate. Normal variation is okay. It's tolerable. We can live with normal variation. It's the abnormal variation that we want to stay away from. And sometimes you get a perfect storm where you get a little bit of normal variation on one extreme and another normal variation on another extreme, and 1 + 1 = 4. That kind of perfect storm. The ready mix producer has quality control technicians and quality control managers and operations managers. So they're responsible for the quality control. So they have a large control over the variability based on the variability of their quality and their processes. The testing agency does have a contribution to the standard deviation, and you can measure the testing lab's contribution. Luke Snell and Karthik Abla developed a Excel spreadsheet. You go and you enter all of the test data from the project, and it will identify the technicians that are having too much variation in their 28-day cylinders. Now, we tend to only look at the 28-day strength test result. We don't very often look at the individual cylinder results that comprised that strength test result. I can remember being on a job down in Mesa Verde, supplied by Four Corners Ready Mix, and everybody was concerned that this 4,500 PSI concrete was only making 4,200 PSI. And when we dug into the data, we found the 28-day cylinders, most of the sets of cylinders had ranges of 1,200 PSI in the 4 cylinders that they used to average to calculate the 28-day strength. 1,200 PSI difference in age of cylinders. The testing lab manager should have been the first one that said, I got a problem. But too many people just focus on the 28-day strength and they don't dig into the data. But if you want, I can email you that spreadsheet that Karthik Abla and Luke Snell developed. And I did this for Stephen Harold at Aggregate Industries, where we were doing a job and it just was generating hundreds and hundreds of test reports. And the quality of the testing was very good. but there were two technicians that software identified as two guys that maybe might want to go look for a different line of work. And that happens. Not everybody is good at making cylinders. Not everybody is diligent at adhering to standards. So that's a good question. So everybody has a contribution to overall variation, and it's how well you manage that variation. If a normal standard deviation for ready mix along the Front Range, I would say it's probably 450 psi, maybe 450 to 550. That's pretty normal. It's pretty tough to get under that. Now, would we like to be lower? Yeah, we would love to have lower variation than that. We have to have a lot of things fall into place to do that. And that's, you kind of get to the point where you can't let perfect be the enemy of good.
Gotcha.
I'll actually add to that, Kevin, just in regards to the question of, it's like, how do you reduce that variability? And it's something that you had said, and we continue to say in almost all of our Tech Tuesdays, is having the conversation up front.
Yes. At
the pre-construction meeting, have that conversation, because it's like we've seen it through our CTAC program that's run nationally. We've seen it through our test fests over many, many years. The initial curing is one of those leading causes of questionable concrete results. And if we're able to reduce those questions just in the initial curing, that variability is going to be reduced in that alone. But that's one of those steps, is just having that conversation right at the beginning.
Yeah. Pre-construction meeting sure beats a post-construction meeting. We chased our tails for a month out on a job in Grand Junction on 29 Road. We saw deviations from standards that we thought might be affecting the low strengths. We corrected those, and a month later, we still had low strength. So we were chasing the wrong problem. So it's best just to do the testing correctly in the first place so you don't draw attention to yourself. It's not always the testing.
Mm-hmm.
Great question, Gabe. Thank you very much. Any other comments or conversations anybody wants to bring up with Kevin here?
I had one more question.
Absolutely.
One of the questions is, I met with an inspector for the city of Colorado Springs, and he was letting me know that this new cement, we were seeing a lot of spalling going on in multiple curb and gutter jobs, I should say, where your water runoff is in the flow line. And we see a lot of delamination and spalling. Is this something new in comparison to what you've seen in the past prior to this, this new mix, these type 2L or TL?
Yeah, that's a really good question. These problems existed when we had C150 type 2 cement. Prior to 2001, we didn't have any limestone in the type 2 cement. After 2001, we started putting up to 5% limestone in it, but we could never get up to that 5% limestone because of the insoluble residue limits and the loss on ignition limits. In 2005, I believe they relaxed the insols and the LOI limits so that we could get closer to 5%. We've had the same problems all the way through, no matter what cement we were using. We've always had scaling. Are the problems worse now? A lot of people think so. I have certainly looked at more scaling in the last year than I probably have in the last 5 years combined. So it's kind of a red flag. Do we have enough data behind us or experience with the 1L cement to say, well, things were better before type 1L cement? I don't think we have enough years under it yet. We can't give up on it. I don't think the industry is going to go back to C150 cement. We have to learn how to use the type 1L cement. Like I said before, if construction practices weren't important before, they sure are now. Not to blame everything on the contractors, but the attributes of type 1L cement, they have a lot of good attributes, but they also have some negative attributes. And one, they can bleed a lot less. And if your concrete doesn't bleed as much, a lot of finishers will resort to blessing the surface of the concrete, which weakens the paste at the very surface. And then you end up with a weaker top. If they don't bless the surface, they end up with plastic shrinkage cracking. So yeah, it's a pretty complex problem. In fact, tomorrow I go right back out in the field with a customer. We're going to look at exactly what you just talked about, scaling, more scaling. So I would say we have more of it now. Did we have a worse winter last winter than previous? Don't know. It seemed like a pretty ordinary winter to me. I just think that top 3 millimeters, it doesn't really, it's the concrete we're making is good quality concrete because the bulk concrete that's in place is good. It's really just the top 3 millimeters is where we're seeing the problem. We've got to figure out a way to correct it.
Sure. Thank you, Kevin.
I heard, I've got a quote from, I believe it was Patrick Matchy at NRMCA that stated, "We've been working with type 1-2 cements for 200 years. We've been working with 1L cements for 2. We've got a long way ahead of us before we understand how to run these processes." Second to that is that all of the construction processes that Kevin just mentioned, we're doing all the same things. Contractors, flat work guys, producers, everybody on the construction site are doing the same processes they were 5 years ago, 10 years ago, 25 years ago. And we're working with a different material. So with this different material, we're exposing a lot of the shortcuts that worked for so many years. So we've got to work through those, figure out what works, what doesn't, and improve what we've been doing.
Yeah, one of the, if you look back at the ACI 308 guidance document on curing, that document was written before type 1L cements. And one of the practices they recommend is initial curing. And I'm not talking about initial curing of the concrete test specimens. I'm talking about the curing you do for the concrete before your final curing. And with pavements, with slip-form pavements, pretty easy because your final curing happens 10, 15 minutes after the concrete's been on the ground. For your industrial floor slabs or sidewalks and curbs and gutter, there's no initial curing. That it's really challenging to do initial curing because you have to work the concrete well before you do your final curing. And in most instances, by the time you get to your final curing, the problem has already manifested itself and it's too late. So this term initial curing, initial curing of the concrete in advance of the final curing. I think that's our biggest challenge. How do we properly initial cure the concrete? Again, I'm not talking about the test specimens. I'm talking about the actual cast in place concrete.
Give you guys just a chance to ask any other questions. Otherwise, thank you very much.
Thank you for your time, everybody.
All right.
Enjoyed it.
Thank you guys. I appreciate it.